Assalamu alaikum and hello students. This is our lecture on static fluids. In this lecture we will study two topics, fluids and Pascal's principle, and two subtopics which are density of a fluid and pressure of a fluid. So first, what are fluids actually? Fluids are the substances that flow. So a fluid is a substance that can flow, and the property of substance is that it conforms to the boundary of any container in which we put them. So if we have a container smaller or larger and of any shape, the fluids will take the shape of the vessel or the container in which we put them in. Like water, if we put them in a cylindrical glass, it acquires that shape. If we put them in a rectangular glass, it takes that shape, or if we put them in a pan, it takes that shape. So it conforms to the boundaries of the container. And there are two types of fluids, compressible and incompressible. So fluids are liquids and gases both, because gas flows and liquid also flows, so both are fluids. One of them is compressible and one of them is incompressible. So the compressible fluids are those which can be compressed, and incompressible are those which cannot be compressed. So gases and liquids. Gases are compressible fluids and liquids are incompressible fluids. We can compress gas, we can compress air, but we cannot compress water or milk or honey. So liquids are incompressible fluids and gases are compressible fluids. Okay, the density of a fluid. The density of a fluid can be different at different points. For example, gases can be dense at certain parts and rare at other parts. So density is represented with this Greek letter rho, and it is represented like this. So small this delta m and delta v mentions about small patches of the volume and mass in that volume. So delta m divided by delta v, by definition you know that density is equal to mass per unit volume. So delta m is the small mass and within the small volume delta v. So delta V is actually the volume element around that point, and delta M is mass of the fluid contained within this volume delta V. And in general form we can write it like this: rho is equal to M over V. V is the volume and M is the mass contained within this volume. Okay, now the pressure, the pressure of a fluid. Let us consider this container. It is a square container and there is a gas filled within it. So if we place a small pressure sensor like this one, which is zoomed in to show a better picture of it. So this is the small pressure sensor. It is actually, its construction is like this. So it will show some pressure that is being exerted by this surrounding gas molecules on it. Means it will sense some pressure. It is made like this. It is a cylinder, okay, and there is a piston in it which can be moved up and down, and below it is vacuum, means that there is no gas present in this area. Only there is a spring which is holding it against the outside pressure. So if there is some pressure on top of this piston, it will definitely go downward. So that movement, the downward movement, shows that there is a pressure. If the area of this piston is represented with delta A and the force that is exerted by the surrounding gas molecules on it is delta F, then if the fluid, this fluid, a gas, exerts delta F force on this piston that has an area of delta A, the pressure P can be given like this. You know what pressure, the definition of pressure, it is the force per unit area. So delta F is the force exerted by um, the fluid on the piston of area delta A. So this delta F is the force exerted on delta A area. And we consider that the force is uniformly distributed over that flat area, then the pressure will be given as F divided by A. So F is the magnitude of the normal force on the area A. This is the general form of the pressure exerted by the fluid. So force exerted on the uniform force. It must be noted that the force must be uniform on an area A. Its units are newtons per meter square because the unit of force is Newton and the unit of area is meter square. Okay, so Newton meter square or Pascal. So these are the units. There are some other units also. The atmospheric pressure is the approximate average pressure of the atmosphere at sea level. What is the atmosphere? All the fluids surrounding the earth, the gases which are surrounding the earth is the atmosphere, starting from the sea level until the space starts. So that thickness of the atmosphere or the thickness of those gases, we also call it the column of the gases from the surface of the earth or the sea level until the space. So the pressure exerted by, because there will be a difference in density at different locations in the atmosphere, so we call it average approximate pressure. So that pressure is called as atmospheric pressure at sea level. Okay, because as we go up, that pressure starts to reduce. The term atmospheric pressure refers to the pressure, average atmospheric pressure of the average approximate pressure of the atmosphere at sea level, not above that. Okay, and not below that either. So this atmospheric pressure term refers to the average approximate pressure of the atmosphere at the sea level. Its unit is 1 atm. 1 atm means 1 atmospheric pressure, which is equal to 1 10 raised to the power 5 pascals, and it is equal to 760 torrs, which is equal to 14.7 pounds per square inches. So these are the conversions of atmospheric pressure from one unit into another unit. And here torr is actually millimeters of mercury. This is the millimeters of mercury is the former name of torr, and psi, pounds per square inch, is the abbreviation, abbreviation of this unit, because this is pound and this is square inches. So pound square inches or psi, you must have seen this written on some pressure gauges, psi, pounds per square inch. So millimeters of mercury is used in some gauges also, some pressure gauges also. In next couple of slides I will show you why millimeters of mercury. Millimeter is length, right, and mercury is an element. Okay, now pressure due to a static fluid. Static fluid is a fluid which is at rest, it is not moving. So pressure of a fluid at rest, or the pressure due to static fluid. Let us consider this container that contains water in it, and there is air on the top of it. So there is an interface between air and water, this one. So the liquid is down below it, and gas or air is on the top of it, and the water surface is considered as 0. Y is equal to 0. We start measuring depth from here, and in this within this water we consider a small patch of water. Okay, so we have considered just pointed out or just labeled this one that we are going to do some calculations on this part of the water. So the bottom part of this rectangular patch, we consider it at depth y2, and the top part we consider it at depth y1. Okay, we're calling it a sample just to make some calculations. So y2 is the depth of the bottom part, and y1 is the depth of the top part of this small sample. Now there are three forces acting on this patch. On the top surface there is the pressure or the force, the downward force because of the water volume of the water on top of it, and then there is an upward force on the lower part of it because of the water below this surface. Okay, and the third one is the weight of this part or sample of water. So if this is if we consider this as a body, there it must have a weight, so the gravitational pull downwards, this is the third force acting on it. So if we draw a free body diagram, it will look like this. So this is this dot represents this sample here, okay, and there are two forces downwards, one is the weight and another one is the force because of the water volume on top of it. Okay, this is the F1 force downwards, and there is one upward force which is because of the water volume below this surface. Okay, so since this part is not moving, it is stationary here, means that the net force, the net force acting on it must be equal to 0, means the upward forces must be equal to the sum of the downward forces, right? So these forces must balance each other. Therefore F2 must be equal to F1 plus mg, right? Because this sample is at rest, it is not moving downwards or upwards or leftwards or rightwards, it's not moving anywhere, it is balanced here, means that all the forces acting downwards are balanced by all the forces acting in upwards direction. So after drawing a free body diagram, we can see that F2 should be equal to the sum of F1 and mg. Now we can write it like this: F2 is equal to F1 plus mg. Now we can put the values of F1 and F2 here as we saw previously. How? Because pressure was equal to F over A, right? So from there we can rearrange terms to find F. F must be equal to P times A, because P was equal to F over A or F divided by A, therefore F will be equal to P times A. So F1 was the force acting on the top surface of the sample, and we consider that at that level the pressure of the fluid was P1, okay, but the area will remain the same, and at the lower part the pressure was P2 but the area was same. So the area of the patch of the sample remains the same, but on the top surface the pressure is P1, and on the bottom surface or floor of that sample the pressure is P2. Okay, since we know that rho m is equal to rho v, actually from the previous slide we know that density rho is equal to m over v, right? So from there we can rearrange our terms to find the value for m. M is equal to rho v, right? So The rho is the density of the fluid here, water density of water in this case, and V is the volume, and you know volume can be written as area times length, right? So we can write like this: rho V is area times length. So A is the area of this part, okay, and also this part, and this is the length, y1 minus y2. This is the length. Y1 is the depth of the top part, and y2 is the depth of the bottom part of this rectangular sample. So the length will be equal to the difference between y1 and y2. You can also consider them as y coordinates. So that's why we can write volume in terms of area times length. Now we can put this value in this equation and we get F2 is P2 times A, F1 is P1 times A, plus mg is equal to this one, rho A g y1 minus y2. So this is, from here, from this equation we can factor out A here, as we can take A common from these two terms, which will be cancelled out with A on the left hand side, and we will be left with this equation: P2 is equal to P1 plus rho g y1 minus y2. This is the height, this one, this height, and P2 is the pressure at this lower level, this bottom level. Okay, so P2 belongs to the bottom level, the pressure at this level here. We can say that this is the expression for the pressure at the lower part of this sample. If you want to find out the pressure for on the upper part, on this upper surface of this sample, we can rearrange our terms to find the value for P1. P1 goes here, P2 goes here, okay, or this whole term goes to other side and P1 stays here. Okay, now using this equation we can calculate the pressure at a certain depth below the water surface. So pressure at depth h in the liquid. So we have to just rearrange our the same example, that our sample was here previously, the rectangular sample here. We just consider that we have moved it to the surface. So the upper one, where the y1 surface, that is not touching the surface of the water here, and this is y2. We just consider it that way, so that the expression that we found in the previous slide can be easily used in this case. So there y1, the upper surface, is now on the surface of the water, and here y is equal to 0, therefore y1 is equal to 0, and here p is equal to p naught, means the p1 was the pressure on the upper surface, right? So this upper surface has pressure of p naught. Why? This p naught is actually the atmospheric pressure because of the air on the top of this water surface. So that is the atmospheric pressure represented with P naught here. And the bottom one, y2, this y2, the bottom surface is at the depth y2, which is equal to y minus h, because this is 0, the surface is 0, and below it all the values will be negative. So this is at, let's say this is h, the magnitude is h, so we call it minus h here. So it is deep. So this negative shows that it is deep into the water by how much depth? H. And the pressure at this level, at depth h from the surface of the water, is P. This is the pressure at the level h below the water surface. Therefore, using that equation, the previous one, we can write that, because just remember that, try to recall, that was P2 is equal to P1 plus rho g y1 minus y2. So P2 is equal to P and P1 is equal to P naught plus rho g as it is, and Y1 minus Y2 is now H, because Y1 is 0 minus H means it is H. 0 minus H is 0 plus H. It becomes H. Therefore, from this equation we can say that the pressure at a point in a fluid in static equilibrium, means this static fluid, depends only on the depth of that point and not on the horizontal dimensions of the container. Means that from this equation we can say that the pressure at a certain depth h at a certain point depends only on the depth of that point, this vertical column only, and it does not depend on the horizontal dimension. So if we remove these boundaries or extend those into a very wide tub or a swimming pool, it will not depend on the dimension of the swimming pool, it will only depend on the depth from the surface of the water. Okay. So this is called as actually the absolute or total pressure at this point, P naught plus rho gh at the depth h. So this is the total or absolute pressure at this point. There is another pressure, we call it the gauge pressure, and the gauge pressure is actually the difference between the total and atmospheric pressure. You remember this P naught here, this is the atmospheric pressure and this is the total pressure. If we subtract them, means P minus P naught, we will get a new pressure, we call it gauge pressure, this one. So from the same example, this one we bring this on the other side, it becomes P minus P naught is equal to rho gh, and it is represented with P underscore G. This is the gauge pressure, which is the difference between the total pressure and the atmospheric pressure. Okay, now let us find out the pressure outside the water at this level 3. This was level 1, this was level 2. We have calculated pressure at level 2 recently. Now we are going to calculate pressure at level 3. At level 1 we already know this is the pressure P naught, the atmospheric pressure. Okay, now we are going to calculate pressure at level 3, which is at D height above the water level. Okay, at this level here, the top surface, this one y1 is equal to 0 and P1 is equal to P naught, this one atmospheric pressure, and y2 is at height D. Okay, so this is the height D, and pressure at this level we just call it P underscore D, because this is at the height of D from the water level. And the density rho is rho air, just to differentiate from the density of the water. Okay, so this is the density of the air at this level. So we have the density of air changes, you know that at the sea level it is different, and on the top of a mountain this is different, right? So here we consider that this is rho air at this level at a certain height D. Now we can write our expression as before. This one was P2 is equal to P1 minus rho GH. Now P2 is replaced with PD, this one here at this level, and P1 is replaced with P naught at this level, at the level of the water, minus rho GH. H here, rho is replaced with rho air, G remains the same, and H is replaced with D. Okay, because earlier it was H, now the height is D. So it can be replaced like this. So this is the pressure at height D above the water level. Okay, now Mercury Barometer. Barometer is a device that is used to measure atmospheric pressure. So this is a barometer actually. It is a very simple barometer, which is simply an inverted tube into a container filled with vessel. And there are graduations on it in millimeters. So this column of mercury, the height of this column is measured in millimeters of mercury. That is why there is one unit that you saw before is millimeters of mercury, that refers to this device here. So if you compare this with the previous example, this is a level 2 where the atmospheric pressure is, and this is the mercury level at a certain height h. So on top of it, there are only it is filled with a few, means the vapors of mercury, and the pressure is so low that we can essentially neglect it and means consider it as zero pressure here. So this is the level 1 and this is the level 2. Compare it with previous examples and we can write the equation that we saw on just the on the last slide, that was equal to P2 is equal to P1 minus rho GH, right? So P2 here, from here you can see it is 0. So 0 is equal to, and P1 here is P0. So we write it here because this is atmospheric pressure. Rho G and H. H is this height of the mercury column here, this one. So from there we can write P0 is equal to rho G H, this one. This is another type of mercury barometer. The purpose of it is also the same. It also measures the atmospheric pressure in the surroundings. It does not depend on the volume, it just depends on the height of the mercury column. It is measured from here until here, right? So the purpose of both is the same. Okay, now open tube manometer. This open tube manometer is actually another pressure measurement device which actually measures the pressure of a gas or the fluid. It measures actually the gauge pressure. There are two types of pressures we saw before, right? Gauge pressure means the total pressure, atmospheric pressure, and the third one is gauge pressure. So total pressure or absolute pressure minus atmospheric pressure becomes the gauge pressure, right? So here in this one, this tube of it is filled with fluid, a liquid, can be an oil here, and this is the gas of which we want to measure the gauge pressure. So this tube is connected with this cylinder or tank of the gas. So on one side of this tube is this, the other side, this side is open, so it is exposed to atmosphere. So this side, it has the atmospheric pressure on this surface, level 1, and on level 2 we have this gas pressure. So the difference between these two levels actually shows which pressure is higher, of course. So since our gauge pressure is equal to the difference between the total pressure and the atmospheric pressure, if this gas has a higher pressure, it will push it downwards, and the level and the difference between these two will increase. It will go down, it will go up, and the difference will increase. And if this pressure, atmospheric pressure, is higher, it will push this liquid down and it may eventually flow into it. So it is, that if in this example here, y1 is at 0, this one, and P1 is at this level is the atmospheric pressure, which is represented with P naught, and Y2 here in the level 2 it is minus H, because we take this one as reference, so it is here minus H, and P2 here at this stage is the total pressure P, or yes, the total pressure at this stage means on this level here. Therefore, by using the equation of the gauge pressure, we can write Pg is equal to P minus P naught is equal to rho Ga. Can be positive, or this gauge pressure can be positive or negative. How? If this total pressure is larger than the atmospheric pressure, then this value will be positive. Okay, and if this pressure, the total pressure, is less than the atmospheric pressure, then this value will be negative, because smaller value, if larger value is subtracted from a smaller value, the result is negative. Therefore, the gauge pressure can be positive or negative. When P is smaller than P naught, then it is negative. If P is larger than P naught, then the gauge pressure is positive. There are examples for it from our daily life. One example is the inflated tires, or human circulatory system, means the blood circulation system in the human body. The absolute pressure is greater than the atmospheric pressure. Therefore, in both of these, so therefore the gauge pressure in this case is positive. And in another example, if you suck on a straw to pull the fluid, for example you are drinking juice or you are drinking milkshake or something through a straw, you pull the fluid inwards. So in that means when you're doing that, the absolute pressure in your lungs is actually less than the atmospheric pressure. That is why the fluid, for example, this is the fluid, this is a glass, and this is your mouth. You are sucking in. Why? How can you suck in? Because when you reduce the pressure of your lungs, then this pressure increases and it goes into your lungs. Then the gauge pressure in that case is negative, when your lungs have actually less pressure than the atmospheric pressure, because atmospheric pressure is the pressure on the fluid that you are drinking, right? You haven't made a vacuum on the top of it, so all the atmospheric pressure on top of the glass on the surface of the fluid is trying to push it downwards, and when it sees a smaller pressure in your lungs, it starts to go into your mouth. And in that condition, in that case, in that situation, the gauge pressure is negative. Okay, Pascal's principle. This is very important principle which has many applications, important applications in our lives. So, a change in pressure applied on an enclosed incompressible fluid, enclosed and incompressible fluid, is transmitted undiminished to every portion of the fluid and to walls of its container. So this is the statement of Pascal's principle. It is saying that if there is a change in the pressure applied, means there was a certain pressure, we changed it to a certain value, by a certain value means we increased it or decreased it, onto an enclosed incompressible fluid. Okay, so this is not gas. Incompressible fluid is transmitted, that is transmitted undiminished, without any change, without any reduction, to every portion of the fluid. So it goes the same change in pressure goes through every portion of the fluid and on the walls of the container without any reduction in it. Okay, for example, when you squeeze your toothpaste, it comes out. So this squeezing, by squeezing you are changing the applied pressure on the tube. Earlier there was atmospheric pressure, then you changed it. By changing the pressure, the same pressure, the change in pressure was experienced by the toothpaste inside it and on the walls of the container also, and it comes out onto your. So here is a example to demonstrate Pascal's principle. Let us consider that we have a liquid which is incompressible fluid inside this container, and this container is fitted with a piston which can move up and down, and there is a small container to put some weight on this fluid, and we are going to measure pressure here at point P, which is at a certain depth H. So at this stage we have placed some lead shorts in it which are exerting a certain pressure, which is Pxt, external pressure, we call it external pressure on the piston, which is also on the liquid underneath it, and the pressure here is equal to P because of the fluid. So this point is experiencing two pressures. One is the pressure because of the liquid on top of it, plus this external pressure because of the weight of the lead shards. Now let us consider we increase this. Now we have increased lead shards by a small amount. We have added a few more here. By adding a few more here means that we have changed the external pressure. We have increased it a little bit. So according to Pascal's principle, the same amount of change must be transmitted through this whole liquid undiminished and to the walls of the container also. So that small change, if we represent that with delta P external, then the total pressure is now this one plus delta P external. This is a small increment. So this was the original one and this is the additional one. So this one must transmit through the whole liquid and onto the walls of container as well. So this small change is equal to the change in the external pressure. It is independent of rho, g and h. It does not matter what is the density and what is the gravitational acceleration at that place and what is the height of the column. This point must also observe the same change in pressure. How much change? Equal to delta P external. This is what Pascal's principle states, that if there is a small change, that must be equally felt at any point within this fluid and also on the walls. So if a point is here or here or here or here, it does not matter. It should not matter, and this point must experience the same change in or increase or decrease in the pressure as much is increased by the increasing the lead shards here. So it must hold for all points within the liquid as Pascal's principle states. So this one is an example of the practical application of Pascal's principle. This is a hydraulic lever, or we call it hydraulic lift also. So this one is filled with oil. It has two openings, one on this side, one on the other side, and both they are different in diameter. So one is wider and one is narrower. So the narrower side is actually the input side and wider is usually the output side. And in this arrangement there are pistons on either side, and there is an incompressible fluid which is oil filled in this tube, and both sides are covered with pistons. So if we increase pressure or we put some more force on this side, by increasing force means that we are increasing pressure. So by increasing that pressure on this side of fluid, it must transmits through the whole incompressible fluid and on the walls of the container also, and on this piston as well. And if this piston is movable, it will move upwards. So let us consider that we have increased the pressure here and that is Fi by putting a force of Fi, and the area of this piston is Ai. Therefore the pressure on this side on this piston will be equal to F divided by I, right? So Fi over Ai. I represent input because this is the input side. We put force on this side and we get output on the other side. So let us consider we have changed the pressure by exerting Fi on Ai. So this is a change in pressure on the input side. So according to Pascal's law, we must experience same change in pressure on the output side also. So these two must be equal. F naught is the output force, okay, with this this piston is pushing upward, and A naught is the area of this piston. So the pressure on this piston will be equal to F naught divided by A naught, right? And the pressure here is equal to Fi divided by Ai. So according to Pascal's principle, both of them must be equal. Okay, from here we can drive our output force. We can rearrange terms to get the value of output force here. It becomes Fi here, okay, times A naught divided by A1. And if A naught, or the area of the output piston, is larger than the area of the input piston, then the output force will be much larger than the input force. That means using this arrangement we can lift very heavy weights by putting very small force. Just like in the workshops, they can lift very heavy cars using this type of device there, the hydraulic lever or the hydraulic lift. So just by increasing the area of the output piston and decreasing the area of the input piston, we can lift very heavy weights by applying very small force. For a downward displacement di of the piston, this one means we have pushed this piston from here until here. The liquid volume displaced is V. So from here, because this is a small piston, the volume displaced is V from here until here. So that V will be equal to area times length, Ai times di. We can write that volume like this. So this is the volume which is displaced when we push this piston from here until here. Now this same volume will be displaced on the other side also. So the volume displaced on the other side must be equal to A naught times the displacement that this piston makes, that is D naught. This one like this. So you can notice that this displacement is much larger than this displacement. So we can use small force to lift very heavy weights, but we have to make much more displacement here to produce a small displacement on the other side. So from this equation we can write the output displacement, how much this piston will be lifted upwards, is equal to input displacement times input area of the input piston divided by area of the output piston. So if you want to find out how much you will get on the output, how much displacement or how much lift will you get on the output piston, you can use this formula to find that out. And in these conditions the work done will be equal to this, the output on this side. You know that the work done is equal to force times displacement. So F naught times D naught, the force times displacement. because both are in the same direction. That is why cos of 0 will be used, and cos of 0 is equal to 1. So the work done will be equal to F naught times D naught. So the value of F naught is this, and value of D naught is this. So we just replace those values and we get Fi di. This is cancelled with this, and this one is cancelled with this. So Fi di. So the work done here is equal to actually the work done on this side, because Fi is the force on this piston, and di, this one di, is actually the displacement made along this piston, means along this force when the piston is moved downwards. So the work done on this piston was equal to Fi di, and on the output was F naught D naught. So these two works are actually equal. So the work done on the input piston is equal to the work done on the output. Therefore, with a hydraulic lever, a given force applied over a given distance can be transformed into a greater force applied over a smaller distance. So smaller force on a larger distance can be transmitted to a greater force but smaller distance. This is all for today. If you have any question, we can discuss during our live session.